Hello everyone, welcome to this video which is entitled Lecture 11, Star Formation and Evolution. In the previous lecture we talked about how solar systems form, our own solar system as well as others in the galaxy and the universe. In this video we're going to talk about how stars form, and in part the basic picture is the same. But in addition we're going to continue this thought process and talk about how stars mature into stable stars, middle-aged stars like our sun, and then how they evolve and eventually die. Let's first start by talking about what is called the interstellar medium. This is the space in between stars. We haven't quite yet gotten to galaxies in this course. We'll get to that soon. But a galaxy is a giant collection of stars. Actually, I've mentioned that. Galaxies typically have hundreds of billions of stars. There are huge spaces in between stars. For example, the closest star to Earth is around a few light years away. The closest star other than the sun, obviously that's the closest star, is around a few light years away. That means that if you travel at the speed of light from our solar system out to the closest stars, it will take you a few years. And therefore, there's a massive distance between even close stars. And this distance is what we call the interstellar medium, and it's populated by two basic components. One is gas and the other is dust. The gas part consists of individual atoms or small molecules. I mentioned earlier in this course that the vast majority of the elements in the universe are hydrogen and helium. This is for reasons that we will talk about when we get to cosmology later on in the course. Therefore, you might guess that most of this gas is hydrogen and helium, which is true. The dust part consists of what we call dust grains. These are small clumps of atoms and molecules that are around 10 to the minus 7 meters in diameter. Here are examples of gas and dust clouds in the interstellar medium. On the left side here we have two images of the same object. One is in the optical, meaning invisible light. That's what we mean by optical. That's the top one here. And notice that you actually cannot see anything in this region here. This region is black. But if you look at exactly the same region in the infrared part of the electromagnetic spectrum, you can see that there are stars behind it. You can see there's material there. And that's because dust often scatters light. And in particular, it tends to scatter visible light. On the right side here, we have another picture of the interstellar medium with a bunch of gas and dust. Let's talk about how stars are born. Stars have fairly well-defined life cycles. They're born, they mature and evolve, and eventually they die. I mentioned that the basic picture of stellar evolution is the same as that of the evolution of I shouldn't say evolution. The basic picture of stellar formation is the same as that of the formation of solar systems. Solar systems form from giant clouds of gas and dust, and the same goes for stars. In fact, I talked a little bit about how the sun formed when we discussed how the solar system formed. I mentioned to you that the solar system formed from a large cloud of gas and dust, which collapsed under its own gravity. And as it began to collapse, it began to rotate because of conservation of angular momentum. The moment of inertia of the cloud, and by the way, I want to point out this is not a cloud like on Earth. We're talking about gases, hydrogen, helium, and dust. We're not talking about water vapor. But anyway, as the so-called cloud contracted, the moment of inertia decreased, and therefore the angular momentum increased, and the resulting solar system, the protoplanetary disk, and then the solar system began to rotate. At the center of this protoplanetary disk, we have a protostar. this protostar is a locally dense region of the protoplanetary disk, and it's basically a large ball of gas. The pressure inside this protostar increases as the gravity, its own gravity, contracts the sphere, the protostar. This raises the temperature of the protostar, and when the temperature in the center reaches a certain point, this is around 15 million degrees Kelvin or so, fusion can begin. This is a diagram of the process that I was just talking about. We start with a large cloud of gas and dust. Here, this is a cartoon depiction of it. And then eventually we end up with a protoplanetary disk with a protostar in the center, which is a very, as I called it earlier, a locally dense region. It's at the center of the protoplanetary disk, so it's the densest region, which, if the region acquires a large enough temperature and pressure, can become a star. I just want to mention before I continue that we talked about what powers stars, which is nuclear fusion. We discussed this when we talked about the sun, and I mentioned that the core of the sun is the region in which nuclear fusion is taking place. And this is a process by which hydrogen atoms, and really we're talking about the nuclei, so therefore just protons, are fused together. They're forced together through tremendous temperatures and pressures to produce heavier elements, and that releases tons of energy. So this is the process that begins in the protostar as the temperature and pressure reach sufficient amounts. Let's talk about nebulae. I've actually used the word nebula or nebulae in this course, and I mentioned that a nebula is a large cloud of gas and dust. But I want to be a bit more specific now and show you some pictures and then talk about some different kinds of clouds of gas and dust. An emission nebula is a large cloud of gas and dust. To use that phrase I keep using over and over, over and over, excuse me, that is illuminated by a lot of hot young stars that are being formed from different parts of this nebula. Excuse me, and this is called an emission nebula because the gases, the dust, are heated up, and when, as you know, when you heat up gas, for example, it tends to glow and it produces an emission spectrum. This is one such example, this picture that you're seeing here. Excuse me. Here's another example of an emission nebula. This is called the Eagle Nebula. This is a very famous picture in astronomy, and particularly it's a famous picture from the Hubble telescope. And it is from, just want to say one more thing before we continue, it is from these regions that stars are formed. This picture here, the Eagle Nebula, contains vast quantities of hydrogen, as well as helium and some other elements. And this region here can form locally dense parts where the mass density is relatively large, and that can go on to form solar systems and stars. Okay, we'll talk more about that a little bit later. Let's continue with the life cycles of stars. Let's talk about the specifics of masses of protostars. If a protostar has a mass greater than about 0.08 solar masses, where solar mass is the mass of the sun, nuclear fusion can occur. I mentioned to you that the pressures and temperatures inside the star have to reach certain values. And this occurs when the protostar roughly has a mass a little bit less than 1/10 the mass of the sun. A star in which nuclear fusion never commences is called a brown dwarf. Brown dwarfs are very cold for stars, not cold in the sense of the Arctic, not cold in that sense, you wouldn't feel that they're cold, but relative to main sequence stars, for example, the sun, brown dwarfs are very cold. A star that has a sufficient mass for fusion, which is what I was talking about in the first bullet point, will eventually become what we call a main sequence star. A main sequence star is a typical middle-aged star. This is a star that's reached adulthood. A young stellar object is a star that is in the early stages of evolution. This could be a protostar or even a pre-main sequence star. Let's go back to the idea of hydrostatic equilibrium. This is an idea that I talked about when we discussed the sun. I said that the sun is very stable because the pressure that is exerted outward from the core due to nuclear fusion is balanced by the gravity of the sun. The sun is basically a large thermonuclear bomb, if you like. It's not a bomb per se. It's not, of course, designed to be a weapon, but you can think of it like that. But of course, it doesn't explode because the sun has a tremendous gravity, gravitational pull, and when these two things are balanced, the sun or the star in general is said to be in hydrostatic equilibrium. This is one of the primary characteristics of a main sequence star. When a star reaches adulthood, sort of like a person, hopefully it reaches hydrostatic equilibrium. Making an analogy to a person, for example, as you become older, you eventually get a career, etc., family, whatever, but you reach hopefully some kind of stable point. I say hopefully, but that's a matter of opinion, of course. But anyway, certainly for stars, when they reach their adulthood, they reach this stable point where they're in hydrostatic equilibrium. The lifetime of a star is determined primarily by its mass. This is a way in which stars are not like people. This analogy is very imperfect. When you're born, your mass doesn't determine your life. Hopefully, you have other aspects of your environment which determine opportunities and whatnot. But for a star, the future is really determined by its mass. More massive stars live shorter, hotter lives, and stars that have low masses live longer, but they also have lower temperatures. This is just to remind you that of what hydrostatic equilibrium is, and also to remind you of a similar slide in the lecture where we talked about the sun. Notice here that we have a depiction of the sun, or this is any star really, not just the sun. The pink arrows represent the pressure pushing outward from the core, which comes from nuclear fusion, and then the green arrows represent gravity pulling inwards. I want to go over once again fusion and fission, but to do so I would like to show you this reasonably quick video from Scientific American. I'm going to post this on Blackboard, so when you get to this point in the lecture, please stop this video and go watch the fission and fusion video on Blackboard. The link should be on the same page where you found this link, and then when you're done, come back to the same point. Let's continue with stars' life cycles. I mentioned that the lifetime of a star is determined by its mass. Massive stars live very short lives. In the very extreme cases, extremely massive stars could live only a matter of millions of years, maybe tens of millions of years, more realistically. Whereas stars that have the mass around the sun will live around 10 billion years. So we're talking about a difference between 10 million and 10 billion. That's a factor of 1,000. And stars that are even less massive than the sun can live longer than the age of the universe, or even longer than that, actually. Let's talk about what happens when a star runs out of its so-called fuel. I'm going to use the term fuel, although I want to emphasize here that usually fuel is used to refer to some liquid usually, or it could be solid fuel that is used in chemical reactions. That's usually the way it's used, like rocket fuel or fuel for your car, etc. In this case, this fuel is not being used for a chemical reaction, like gasoline or rocket fuel. This is fuel for fission. For fusion. I'm sorry, I had fission on the mind. This is fuel for fusion. So it's not fuel in the typical colloquial sense. By fuel, I just mean hydrogen. But I'm going to use the term advisedly here. So anyway, stars that are very large and very massive end up fusing hydrogen at tremendously high rates compared to small stars. And they fuse hydrogen so rapidly that they can run out of hydrogen in their cores, not in general, but just in the core of the star, even after just a matter of millions of years. When a star, whether it's big or small, runs out of hydrogen in the core, and when this hydrogen has been turned into helium, this star transitions into old age, and the star becomes a red giant. A red giant has a low temperature but high luminosity. It's found near the top right or top center of the HR diagram. A red giant is exactly what it sounds like. It's a giant star, but it's red, so it's cool. This star moves off the main sequence. It's no longer a sort of middle-aged star. It's moving into what you could call old age or retirement as far as the star is concerned. The helium core then begins to fuse, producing heavier elements. The idea behind fusion, remember, is that you start with a relatively low, in the case of a star, you start with hydrogen, a low mass element, and you fuse the hydrogen up to a higher mass element, helium, but you can continue. You can fuse helium and you can go all the way up to iron. Well, we'll get to that a little bit. So you can keep going, and the red giant is going to then fuse helium, producing heavier elements. And stars with a mass of less than about 0.8 solar masses require longer than the age of the universe to become red giants. So we don't see any red giants that come from stars that have masses less than about 0.8 solar masses. The age of the universe, by the way, is almost 14 billion years, which we'll get to when we talk about cosmology. Let's discuss the evolutionary track of stars on the HR diagram. Hopefully you remember the HR diagram. This is a depiction of stars as depiction of stars in a 2D plot by categorizing stars via their luminosities and surface temperatures. That's what I was trying to say, not very articulately. So if we plot the stars we find in the universe by luminosity, where luminosity increases from bottom to top, and then by temperature, where temperature decreases from left to right, we end up with the HR diagram. The main sequence is this S-shaped curve here, and these are typical middle-aged stars like our sun that have become adults, so to speak, in the stellar sense, and are in hydrostatic equilibrium. Our sun is somewhere around here on the main sequence. When our sun runs out of hydrogen in its core, it will become a red giant. It will move off the main sequence, therefore, and it will follow roughly this path and become a red giant. Here we have exactly the same plot, except that we have different paths for different stars of different masses. The sun is here. This means the mass of the sun. This is one stellar mass. This symbol down here, the circle with a dot in it, refers to the sun. Notice that we have a star 4 times more massive than the sun here, and then 10 times here. These elements correspond to the points on the tracks where those elements begin to fuse in the core of the star. The more massive a star is, the more massive elements it can produce. Let's talk about what happens when red giants use up their helium stores, so to speak. Okay, so I mentioned that when a star reaches the red giant stage, it begins to fuse helium in its core. And this defines the red giant stage, when the star has run out of hydrogen in the core. Red giants eventually fuse helium into eventually carbon, and if a star is exceptionally large, larger than about 10 solar masses, it can fuse atoms up to iron. It turns out that fusing atoms that have larger and larger masses, generally speaking, takes greater and greater pressures and temperatures. So stars that have less than about 10 solar masses are really going to stop at carbon and really cannot fuse carbon into higher, more massive elements. Whereas if the star begins with greater than about 10 solar masses, it can go all the way up to iron. It turns out that fusing iron into heavier elements is exceptionally difficult and cannot occur under normal circumstances. It can only occur under exceptional circumstances, namely supernovae. But we'll get to that in a little bit. When the core of a red giant runs out of fuel, so to speak, that it can fuse, then the star's outer layers are ejected, and this creates what we call the stellar wind, which we talked about. This is the ejection of charged particles from a star. I've initially talked about this when it comes to the sun, but this would be, we're using now the term stellar wind in a general sense. So this would be a huge ejection of the outer layers of the red giant. These would be gases primarily. This creates what we call a planetary nebula. Unfortunately, a planetary nebula is an object that has nothing to do really with nebula or nebulae and nothing to do with planets. So this is a really bad term. It's a misnomer, so to speak, but unfortunately this is the term we use. A planetary nebula is what's left over after a red giant has its outer layers ejected because it runs out of fuel, so to speak, in its core. And therefore, a planetary nebula consists of the core of the star, which we call a white dwarf, and then the gas that was ejected from the star enveloping it or around the white dwarf. That's a planetary nebula. The core, as I said, is known as a white dwarf, and this is a very hot object, as you can imagine, because it's the core of a star. White dwarfs are very dense. They are roughly the size of Earth, but they have masses up to about 1.4 times the mass of the Sun. So they're incredibly dense objects. It's very hard to explain or convey how dense they really are. So let's do this in terms of gravity. You can look up the number, the density of a white dwarf, but it won't really mean much to you. But we all have had the experience of holding a penny or a nickel or something in our hands. So imagine you're holding a penny in your hand. It doesn't weigh very much on Earth. But suppose that you take that exact penny and you bring it to a white dwarf. On a white dwarf, it would weigh about as much as a car. So on a white dwarf, you would not be able to pick up a penny. It would weigh around 2,000 pounds. This, of course, applies to you. You would weigh a vast amount, right? So you wouldn't be able to live on a white dwarf for many reasons. First, it's way too hot, way too much radiation. But even if, and there's no oxygen, but beyond all those, you would weigh so much that you'd be crushed into oblivion. A white dwarf will just sit there in space with the cloud of gas that was emitted from the star around it, and it will radiate into space. Eventually, a white dwarf will radiate almost all of its energy and it will become a black dwarf, which is exactly the same object, but it's cooler and therefore it doesn't emit as much energy, and so we call it a black dwarf. It's a black dwarf because literally it looks black since there's not much radiation coming from it. Let's talk about a Oh, I'm sorry. Before we get to that, I want to show you some pictures. I'm sorry. I'm getting ahead of myself. I want to show you some pictures of planetary nebulae. This is called the Cat's Eye Nebula. You can see the gases here around the center. These gases are illuminated. They're shining all kinds of beautiful colors in purple and orange and blue, and they're illuminated by the white dwarf at the center. This white dwarf is this object here. It's a very hot, dense core of the star that once was, that now is no longer fusing, it's just a remnant. But the enormous amount of radiation that's emitted by a white dwarf is heating up the gases, and then those gases are emitting light. This creates emission spectra. If you like, this is what I was talking about way back when I talked about if you heat up a gas, it will emit light. This is a good example of that. So the different colors that you see come from the fact that the gases that form the planetary nebula that are surrounding the white dwarf have certain elements in them, and those elements emit light of different wavelengths. That's where these colors are coming from. This is an example of what's called a carbon star, but for the purposes of some time, saving time, I'll skip that example. This is an example of another planetary nebula. Here we have a white dwarf in the center, and then we have this beautiful array of colors from the gas surrounding the white dwarf. Let's talk about what happens when stars die when they're even more massive. Let's get to, in other words, even more and more interesting ways that stars can die. If a star begins its life with a tremendous amount of mass, then it can eventually explode, creating what's called novae. In fact, there's actually different kinds of novae. In some cases, a star doesn't have to begin with a tremendous amount of mass, although those are the most prominent kinds of novae. But okay, we'll get to that. Let's talk about the least spectacular kind of nova, and then we'll get to the more spectacular kind. Let's say that we begin with a binary star system. A binary star system is a star system in which you have two stars. That's what the word binary means. We have two stars that are orbiting each other. And let's say that one is a white dwarf and the other is a main sequence star. The white dwarf, because it has a tremendous density and therefore tremendous gravity, can pull gases from its main sequence partner toward it. This can create an accretion disk. An accretion disk is a disk of gas that's rotating faster and faster around some object that has a large gravitational pull, in this case, a white dwarf. The white dwarf is pulling this hydrogen gas toward itself, and this hydrogen gas will reach the surface of the white dwarf, and the surface of the white dwarf is very hot. If the surface temperature exceeds around 10 million degrees Kelvin, then hydrogen can begin to fuse. And if this hydrogen fuses in large amounts, this is called a nova. We have a sudden explosion of hydrogen because we have a huge amount that's fused. This is the same thing that powers thermonuclear weapons. So we have this massive explosion called a nova, and these gases are ejected out into space. By the way, I think earlier I may have mentioned 15 million degrees Kelvin, but I misspoke. I meant to say 10 million degrees Kelvin. I cannot quite remember the number that I had spoken earlier, but vaguely in my memory I said 15. But fusion occurs around 10 million or so degrees Kelvin. It actually depends on pressures, etc. But anyway, I'll just use, for simplicity, the number of 10 million degrees Kelvin. Okay, so that is what we call a nova. Let's talk about what we call a supernova. In particular, I wanted to talk about a core collapse supernova. This is a much more spectacular explosion. This is the rapid collapse of a star when essentially when fusion has ceased and there's no more hydrostatic equilibrium. There's just gravity pulling the star in. So imagine the sun. Let's think about a thought experiment. We take the sun. There's an enormous amount of force being pushed out, pushing the sun out from the core of the sun. And this is balanced by gravity. The sun has an enormous gravitational pull. Let's assume, for the sake of argument, even though this is not possible, that fusion suddenly stops in the sun, let's say right now. The pressure pushing outward on the sun would suddenly go to zero, but the sun has a tremendous gravity. So the sun would collapse in on itself. Remember, the sun is not like the earth. The earth is made of rock and metal, etc. So the earth cannot collapse in on itself. It's a solid object. It's a terrestrial planet. But the sun is not like that. It's made of gas. So it would collapse in on itself. And then the temperatures and pressures in the center of the sun would increase. This can happen if a star is near the end of its life and the core of the star has fused elements all the way up to iron. I mentioned earlier that iron, as it turns out, is exceptionally hard to fuse. So there's really no star that can fuse iron into heavier elements. When this happens, the pressure pushing outward from fusion suddenly goes to zero, and this can actually happen extremely quickly once the core of the star fuses to iron. This can happen just all this happens in matters of days or hours, and then suddenly the star will collapse in on itself for the reasons I mentioned earlier in our little thought experiment, and this can happen in roughly a second, and then the core of the star reaches a density that is almost unimaginably high. It's about 1,000,000 billion times that of water. This density and the associated temperatures are so great that iron can actually fuse. This is the extraordinary circumstance I mentioned earlier, where iron can fuse into heavier elements, and this produces a massive, what amounts to a thermonuclear explosion that we call a supernova. Okay, I want to show you a picture before we continue. I know I'm doing this out of order, but this is a supernova. This is supernova 1994D. This is a single supernova that I've circled in red. This is a star that has exploded in the way that I was just talking about. And this star is part of a galaxy. I think it's part of this galaxy. And in any case, there's a galaxy here. And this galaxy has billions and billions of stars in it. And it has a center. The center of the galaxy is very dense and emits tons of light. You can see that this one star is emitting about as much light as the entire galaxy. And this galaxy contains hundreds of billions of stars. And so supernovae are tremendously energetic explosions. I want to show you some other pictures and also cartoon depictions of what I was talking about. Let's look at this depiction of novae. I was talking about how a nova can form and also what it is. The idea, remember, is that you have a binary star system. You have a main sequence companion to a white dwarf. These stars are orbiting each other. The white dwarf is stealing gas from the main sequence star, and then this gas is fusing on the surface. This produces explosions, and these are real pictures of novae. This is a black and white photo here, which is not very satisfying. But then we have a color photo of sorts here. So this picture here has the white dwarf and then the accretion disk. And then we can see the disk moving away, being ejected from the star because of fusion that is occurring in the disk due to the extreme temperatures. Let's talk about different types of supernovae. There are actually two types, and unfortunately the naming convention is very confusing. I'm sorry about this, but I shouldn't say sorry, it's not my fault, but nonetheless, this is something that you just have to memorize, and it's rather annoying to do so, but we have a type 2 supernova and then a type 1 supernova. The way to remember this is that a type 2 supernova involves one star, and a type 1 supernova involves two stars. So go figure why that naming convention is the way it is, I don't know. But let's start with a type 2 supernova. A star that begins its life with a mass about 8 times that of the sun will probably explode in what we call a type 2 supernova. This is a process similar to what I discussed earlier. This is I guess we can call it typical supernova in the sense that these are the most spectacular explosions. So when people say supernova, they often mean type 2. In this case, the star becomes a red giant. Its core at that point will have run out of hydrogen, so it has helium in the core. The helium fuses to heavier elements. Those heavier elements fuse all the way up into iron. Once the core is iron, then fusion suddenly stops. The star collapses in on itself. The pressures and temperatures in the iron core become almost unimaginably high. The iron then fuses, and then that creates this extreme explosion. In a type 1 supernova, we start with two stars. It's a similar situation to the nova I talked about earlier. We have a white dwarf with a main sequence partner. And it turns out that if a white dwarf has enough mass, it will actually collapse in on itself. I didn't talk about this a little bit earlier for the sake of time, but there are mass limits to white dwarfs because a white dwarf doesn't fuse. There's no fusion occurring in a white dwarf. It's just a remnant. But white dwarfs are prevented from collapsing by a kind of pressure or force that originates from the kinds of particles that constitute the white dwarf. The technical terms don't matter, but the point is that a white dwarf is a sort of solid object in the sense, and just like trying to crush rock, you have to overcome some forces from the atoms or molecules that make up the rock. A white dwarf is a bit like that, except that it's not made of rock, it's made of a more exotic material. But nonetheless, there are innate forces that resist the compression of a white dwarf. But these forces are not infinite, and if a white dwarf acquires more than about 1.4 times the mass of the sun, which is called the Chandrasekhar mass, named after an Indian physicist, Chandrasekhar, then the white dwarf will collapse, and this is referred to as a type 1 supernova. And this can occur when a white dwarf has a main sequence partner and it's stealing gas from its partner, and then it steals so much gas that its mass becomes greater than about 1.4 times the mass of the sun. So it gobbles up all kinds of mass, and then it collapses in on itself. Supernovae, are so energetic that they can release as much energy in a few months as the sun releases in 10 billion years. 10 billion years of fusion in just a few months. Here is a cartoon depiction of the two types of supernovae I was talking about. The top one is a type 1 supernova involving two stars. Here we have a white dwarf with a partner. The white dwarf is stealing gas from its partner here, which in this case is listed as a red giant, but the white dwarf would need a partner with tons of gas, and then the white dwarf will explode if its mass reaches a certain value. And then we have the type 2 supernova, which involves one star that begins its life with a tremendous amount of mass. And then just to recap, the star becomes a red giant. It reaches the stage where its core is iron, and then it suddenly implodes because fusion stops and then explodes. implodes and then explodes. I showed you a picture earlier of a supernova. Here's another one. This is the remnant of a supernova. The gases here that form this remnant are still hot. Supernovae, as I mentioned, release tremendous amounts of energy. So these gases are still radiating away some of the energy. Let's talk about supernova remnants. I just showed you an example of one. The most famous supernova remnant is that of the Crab Nebula here. This formed from a supernova that probably occurred in 1054 CE, otherwise known as AD. And the reason we think a supernova occurred in this year is because astronomers on Earth actually noted that there was a large star suddenly seen during the day. And in particular, Chinese and Middle Eastern astronomers, who were the most prominent astronomers at the time, mentioned this. And we now know today that the Crab Nebula exists, and we can put two and two together and say that this nebula probably formed about 1,000 years ago. The Crab Nebula, by the way, is not extremely close to us. Actually, off the top of my head, I don't remember the distance, but it's light years away. So actually all of this stuff happened in the past, but we're just seeing it, seeing the effects and seeing the supernova now and then in the past. But in any case, that's why we think that this Crab Nebula is left over from a supernova that actually was observed on Earth about 1,000 years ago. And once again, just to make sure this is clear, this picture is formed from gases that are the remnant of the supernova, and they're still hot and still radiating away some of the energy. This is an example of a planetary nebula, I believe. I was just trying to recall now if this is a planetary nebula, but you can see the, oops, I apologize. My computer is freaking out on me, but you can see the white dwarf in the center here. So this is a white dwarf surrounded by gas that's been ejected from the star. Let's talk about what happens after stars explode. I mentioned to you, and I showed you some pictures of supernova remnants. We can have actually more exotic remnants than just gases, however. If a star begins its life with a mass between about 18 and 20 to 30 solar masses, there's debate about exactly what the upper limit is. That star will probably become a neutron star eventually. That star will become a red giant. It will explode in the type 2 supernovae sense that I talked about. And then the core of the star, or I shouldn't necessarily say the core, but there will remain a remnant of the star that we call a neutron star, which is essentially the core of the star that exploded, shed everything else, but the neutrons that make up the core. And a neutron star is called a neutron star because it's made essentially of neutrons that are stuck together and held together by gravity. A neutron, just in case, just to make sure that we're on the same page here, is a component of a nucleus. Nuclei consist of protons and neutrons, and then an atom consists of a nucleus surrounded by electrons. A neutron is neutral, hence the name neutron. Neutrons are actually formed from quarks. Quarks are what we think are fundamental subatomic particles that make up neutrons and protons. Okay, that's just a little bit of background, but the neutron star consists of just neutrons that are packed together by gravity. And this makes neutron stars tremendously dense, even more dense than white dwarfs. Let's see if we can get a sense of just how dense these neutron stars are. They typically have diameters around 10 kilometers, which means that they're roughly the size of Manhattan Island, but they typically have about 1.4 times the mass of the sun. A neutron star often is very hot. It may have a surface temperature of around 1,000,000 degrees Kelvin, but the core probably has a temperature upwards of about 100 million Kelvin. And let's perform the same thought experiment we did with the white dwarf. We said that if you took a penny to a white dwarf, it would weigh about 2,000 pounds. If you took a penny to the surface of a neutron star, it would weigh about 550 million pounds. If you were to go to a neutron star, you would be crushed into oblivion to such a degree that your body wouldn't even consist of molecules. In fact, it wouldn't even consist of atoms. Your atoms would be crushed down to neutrons. So you'd be a neutron paste that gets attached to the surface of the star. Okay, not a very nice topic, I know, a morbid topic, but let's go on to something even more exotic. If a star begins its life with a mass around 20 to 30 solar masses, 20 to 30 times the mass of the sun, it will very likely produce a black hole. I mentioned earlier that a white dwarf can collapse in on itself to explode. This is a type 1 supernova. This occurs because the white dwarf is prevented from being compressed by intrinsic forces that come from the particles that make up a white dwarf. The details don't matter all that much here, but the point is that the same is true for a neutron star. A neutron star has a tremendous density because it is composed of neutrons that are packed together, and these neutrons are formed from quarks. There is an innate pressure that pushes outward on the neutron star that counteracts gravity. And that's why neutron stars don't collapse in on themselves. It's extremely difficult to take neutrons and compress them together. But it turns out that it's not impossible. If you have an object that has enough mass, then it can actually collapse even a neutron star or something of a similar density, and there's nothing in nature that we know of that can then oppose the collapse to infinity. And this is what's known as a black hole. So if a star produces a remnant after it explodes in a supernova that is too massive, it will collapse into nothingness. It cannot even be a neutron star. And a black hole is called a black hole because nothing can escape it. Actually, there's a little caveat to that, which I'll get to, but basically nothing can escape a black hole. And the reason is that a black hole has such a tremendous gravitational pull that not even light can escape. And the reason light cannot escape is because every object has what's called an escape velocity. This is the minimum velocity you have to escape the gravitational pull of an object. For Earth, I never remember the number, but it's a relatively fast speed. I think it's something like, I don't want to say because I may forget the number. But anyway, Earth has a certain escape velocity. If you want to escape Earth's gravitational pull, you have to orient yourself away from Earth and move with at least this speed. And the speed is much slower than the speed of light, although it's very hard to actually get to the speed. You need advanced equipment, etc. The escape velocity of a white dwarf is even higher. The escape velocity of a neutron star is close to the speed of light, but not the speed of light. But the escape velocity of a black hole is greater than that of the speed of light. So if light gets near a black hole, near the region where the escape velocity is greater than the speed of light, it cannot leave that region. Let's talk about what constitutes a black hole. You might say, okay, the black hole is black and the mass collapses to nothingness, but what exactly is it? Well, we don't know the answer, actually, but in principle, or maybe I should say theoretically, according to our current understanding of physics, all of the matter in the black hole is crushed to a single point in the center of the black hole. This point has no volume, it has no area, it's just one point in space, and this point is called the singularity. Now I say theoretically because few people actually take this seriously. The real answer is we don't know what happens in the center of a black hole, and the reason is that our models of physics are not good enough, basically. They're not complete enough to actually explain to us or predict what happens in the center of a black hole. Our physics breaks down. So we'll need more advanced physics that hopefully we will obtain some time in the future to say what actually the singularity is. But for the purposes of trying to conceptualize a black hole, you can think of it as a single point with the idea that that's the concept that comes from our theories of physics, although we really don't know. Black holes are discovered via their gravitational poles. Another question you might have is, if black holes don't emit any light, how do you discover them? Which is a very good question. And the answer is typically that a black hole is a highly compactified region of space where there is a tremendous amount of mass. And there are often objects orbiting a black hole. So if you see, let's say, a star or a dozen stars orbiting a very tiny region of space that appears to have nothing in it, that is very likely a black hole. And particularly if that region of space contains a mass which is far too large to be a star or a planet or anything like that. An example would be what's called Sagittarius A star, which is the region which we think is a black hole at the center of our galaxy, the Milky Way galaxy. There are, I always forget how many, something on the order of a dozen or more stars orbiting a very small region. This region appears black, doesn't appear to have anything in it, but the stars that are orbiting, or some of them, are quite big, and you can use this information about the sizes of these stars and their speeds and other information to compute the mass of this region. And it turns out the mass of this region is millions of times the mass of the sun, even though it's a tiny region and there appears to be nothing there. So that's very good evidence that there's a black hole in the center of our Milky Way galaxy that we call Sagittarius A star. We will talk about black holes a little bit later in this course. For now, I want to move on to pulsars and magnetars. We're continuing the theme of exotic remnants of stars. When stars die, they produce these bizarre remnants. A pulsar and a magnetar are two examples of neutron stars. In 1967, there was a discovery of a pulse in the sky that was very regular. These two astronomers, Jocelyn Bell and Anthony Hewish, discovered a pulse which occurred every 1.3 seconds in the radio wave part of the spectrum, and it was coming from a particular point in space. And so they humorously named it LGM1, meaning Little Green Men 1. And the reason they gave it this humorous title is because this is similar to the kind of signal that we would expect to see from an extraterrestrial source. Because most of the time when you look out, virtually all the time, when you look out into the universe in radio waves, in other words, you don't literally look with your eyes, but you examine the universe with radio waves, or pretty much any other part of the electromagnetic spectrum, you see static. Sort of like if your radio is not tuned properly, you just get static, you get random noise. If you get a signal which is highly regular, then you begin to think that it was emitted by some radio station somewhere. And so there was the thought that maybe this is an extraterrestrial signal, but it turns out it wasn't. It's just a pulsar. A pulsar is a neutron star that is rotating around very quickly. And it's emitting radiation because they're very hot. And it's emitting radiation in these cones along these trajectories. And if you happen to be in the path of this radiation, then you will notice a blip. You'll notice a detection of this radiation every time the neutron star rotates around once. And that's why these pulses are so regular, because neutron stars are rotating around, and due to the conservation of angular momentum, this rotation is very regular. But now we found many pulsars, so it wasn't ET, and there are pulsars that rotate thousands of times per second, and then some that rotate every roughly 8 seconds or so. So they vary in the rate at which they rotate, but they generally rotate quite quickly. Let's talk about magnetars. A magnetar is a neutron star that has a tremendously great magnetic field. Neutron stars typically have enormous magnetic fields, up to 1 trillion times as strong as those of Earth, typically. But some neutron stars have magnetic fields that are maybe 1,000 times stronger than that, and these are called magnetars. And these magnetic fields are so strong that they emit radiation. Magnetic fields actually contain energy, and 1 cubic centimeter of space near a magnetar would contain as much energy in the form of magnetic fields that is produced by a typical nuclear power plant over an entire year. That's 1 cubic centimeter. A cubic centimeter is roughly the size of, or smaller than a postage stamp, but this is cubic, so it's a volume of space. Actually, a better example would be a cube of sugar. I don't know how many people use cubes of sugar these days, but anyway, a little cube of sugar that you put in your coffee or something is roughly a cubic centimeter. So not a cubic centimeter of the neutron star, of the space around it that has magnetic fields, just the energy of the magnetic fields themselves. And there's no magnetic field that we can produce which is anywhere close to as strong as this, because magnetic fields exert forces on charged particles. And ultimately, everything is made of charged particles. Everything on Earth, anyway, is made of charged particles. We're made of water, which is oxygen and hydrogen, as well as carbon, etc., and a variety of other molecules. But all the molecules and elements, of course, molecules are made of elements, are made of charged particles, electrons, protons, and then there's neutrons, but those aren't charged. But anyway, the protons and electrons are affected by magnetic fields. So if you produce a magnetic field which is tremendously strong, it eventually starts to rip apart all matter that's made of charged particles, which is everything on Earth. And if you tried to produce a magnetic field which is even about 1 billionth as strong as that of a magnetar, you would end up destroying the experiment and any people in the way, because the equipment would actually be ripped apart by the magnetic fields. A magnetar's magnetic field would rip you apart from around 100 miles away. Okay, so once again, a little bit of a morbid topic, but nonetheless, these are truly exotic objects, and it's amazing to think that these things exist out in the universe that are so different and so alien to anything that we know of on Earth. I want you to watch this video on pulsar black hole binary systems that I'm going to post to Blackboard. Thank you for watching this video. I know that it's been quite long. We've covered a lot of slides and a lot of material, but we've talked about how stars form, which is similar to the formation of solar systems, and in the basic conception. And then we talked about the main sequence stars, which are typical stars in their adult lives. And then we talked a lot about how stars die, and they end their lives. Some of them end their lives in fairly mundane ways, and others die in spectacular ways and leave behind remnants that are really strange and exotic. So in any case, thank you for watching this video on Lecture 11, and I will talk to you in another video.